February 7th, 1967. Murmansk, the eastern shore of Kola Bay. At Pier 14 of the Arctic Shipping Administration's primary servicing facility, a vessel that had changed the operational geometry of Arctic navigation was moored alongside a floating technical base for a scheduled maintenance and refueling cycle. The ship was the Lenin. It was the first nuclear-powered surface vessel in the history of maritime engineering. It had been operating for 7 years. It had opened the northern sea route to year-round transit in a way that diesel icebreakers never could. The Soviet state had presented it to the world as proof that Soviet technology was not merely competitive with the West, but ahead of it in the domain that mattered most to Moscow's strategic planners: the capacity to project industrial power into the Arctic. On the morning of February 7th, the senior engineering team overseeing the scheduled fuel replacement in reactor number 2 initiated a procedure they had performed before. They followed the written sequence. They operated within the documented parameters of the OK-150 reactor's maintenance protocol. What happened in the next several hours was not the result of a crew that deviated from procedure. It was the result of a procedure that had a design-level assumption embedded within it. An assumption about the physical state of the reactor's fuel channels that was wrong, and that had been wrong since the Lenin's original reactor system was designed, and that the organization responsible for that system had been warned about in an internal technical review that never reached the people performing the maintenance. The accident that followed was classified immediately. The investigation that followed the accident was classified at a higher level. The damaged reactor compartment from the Lenin would eventually be removed from the ship entirely, transported by barge to the eastern Kara Sea, and sunk in water approximately 30 meters deep. A disposal decision that was also classified, and that would not be officially acknowledged by any Russian government institution for 25 years. The families of the personnel who received radiation exposure during the accident were not given complete information about what had occurred or what the long-term health implications might be. The engineers who had written the internal technical review warning about the design assumption embedded in the refueling procedure were not publicly credited with having been correct. Their analysis sat in a classified filing system inside the OKBM Design Bureau's restricted archive for decades. To understand what the classified investigation actually found, you have to understand why the Soviet Union built the Lenin in the first place, and what the operational requirements of Arctic nuclear propulsion forced its designers to do with reactor architecture that no maritime engineering organization in the world had ever attempted before. The Northern Sea Route is not a route in any conventional sense. It is a corridor, a 5,600-kilometer navigable pathway running along the entire northern coastline of the Soviet Union from the Kara Straits in the west to the Bering Strait in the east. For most of the 20th century, that corridor was navigable for only 4 to 6 weeks per year during the brief Arctic summer, when ice extent reached its annual minimum. In winter, it froze completely. The strategic significance of making that route navigable year-round was not theoretical for Soviet planners. It was existential. The Soviet Union's eastern industrial regions, the enormous mineral extraction and processing infrastructure built across Siberia during the Stalin-era industrialization campaigns, required continuous resupply and the export of raw materials. The overland rail infrastructure connecting European Russia to the Soviet Far East was a logistical bottleneck that could be severed in wartime or crippled by the sheer volume demands of a planned economy operating at peak production. The Northern Sea Route, if it could be kept open continuously, represented a maritime supply line that circumvented those vulnerabilities entirely. Diesel-powered icebreakers could not solve the problem. A diesel icebreaker requires fuel. Refueling in the Arctic requires either shore-based depots or tanker support, infrastructure that adds cost, vulnerability, and operational complexity to every transit. More fundamentally, diesel power plants cannot generate the sustained shaft horsepower required to force a path through multi-year Arctic ice in conditions where the passage is not yet opened. They work at the margins of the sea ice season. They cannot extend that season in a meaningful way. The calculation inside the Soviet Ministry of the Merchant Marine and the Ministry of Medium Machine Building, the institution responsible for Soviet nuclear program development, was straightforward. A nuclear-powered icebreaker does not require refueling in the field. Its operational endurance is measured in years, not days. Its power output is limited by its reactor's thermal capacity, not by the volume of diesel stored in its bunkers. A sufficiently capable nuclear icebreaker plant could theoretically generate enough shaft power to force transit through Arctic ice conditions that no diesel vessel could approach. The mandate issued to the Iceberg Central Design Bureau in Leningrad and to the OKBM Mechanical Engineering Design Bureau in Gorky was precise. Design a nuclear-powered icebreaker capable of maintaining continuous Arctic operations without refueling for extended periods, with a propulsion plant powerful enough to break through multi-year ice at operationally useful speeds. The design that emerged would carry 3 pressurized water reactors, designated the OK150. Each reactor would generate 90 megawatts of thermal power. Together, the 3-reactor plant would deliver 44,000 shaft horsepower to 3 propeller shafts, enough to drive the Lenin's reinforced bow through ice that would stop any diesel vessel in the world. The OK150 was not derived from submarine reactor technology, although it drew on some of the same engineering principles. It was a purpose-designed maritime power plant optimized for a specific operating profile that did not exist in any previous nuclear engineering specification. The Lenin would not operate like a submarine, sealed below the surface with a stable external environment. It would operate on the surface of the Arctic Ocean, exposed to temperature differentials ranging from the normal ambient temperature of the reactor plant's primary coolant circuit to Arctic air temperatures of minus 40 degrees Celsius outside the hull. It would operate continuously for months at a time. It would then dock at a maintenance facility, shut down its reactor plant for servicing and fuel replacement, and return to operational service. That maintenance cycle, the shutdown and refueling sequence, was where the design assumption lived. A pressurized water reactor operates on a principle of deliberate physical containment. The reactor core, where the nuclear fission chain reaction occurs and where thermal energy is generated, is surrounded by a primary coolant circuit. Water in that primary circuit is maintained at high pressure, high enough that it remains liquid even at the temperatures the reactor core produces. This pressurized primary water carries thermal energy from the reactor core to a steam generator, where it transfers heat to a secondary water circuit. That secondary circuit produces steam. The steam drives turbines. The turbines drive the propeller shafts. The primary circuit is sealed. It is a closed loop. The water in it is not supposed to come into contact with anything outside the pressurized boundary of the reactor system. This is not merely an engineering preference. It is the fundamental safety architecture of pressurized water reactor design. The primary coolant in a reactor that has been operating becomes radioactive through a process called neutron activation. Neutrons from the fission reaction interact with trace elements in the coolant water and with the materials of the pipes and components of the primary circuit, producing radioactive isotopes. The primary coolant water of an operating reactor is highly radioactive. Keeping it sealed within its designated circuit boundary is not optional. The OK150 reactors on the Lenin each contain 219 fuel assemblies. Each assembly was a bundle of uranium fuel rods enclosed in a metal cladding, zirconium alloy chosen for its low neutron absorption characteristics and its resistance to corrosion in hot pressurized water. The fuel assembly sat inside a reactor vessel, a thick-walled steel cylinder filled with pressurized water, and were held in precise geometric arrangement by structural support grids that maintained the spacing required for the chain reaction to sustain itself at the designed power level. When the fuel was exhausted after its operational cycle, it had to be removed and replaced. This was the refueling operation. The refueling procedure for the OK150 required the reactor to be shut down. The fission chain reaction halted by insertion of neutron-absorbing control rods. After shutdown, the reactor core continued to generate heat from the radioactive decay of fission products inside the fuel assemblies. This decay heat is not optional. It is a physical consequence of operating a reactor. It cannot be stopped by inserting control rods. For a period of days after shutdown, the OK150 core had to continue to be cooled by circulating water through the primary circuit to prevent the fuel assemblies from overheating. The refueling procedure required that the fuel assemblies be removed from the reactor vessel one at a time, using a specialized handling machine that could reach into the vessel through an access port in the reactor's upper structure. Each assembly had to be grasped by the handling machine, lifted free of the support grid, moved to an intermediate storage position within the shielded refueling cavity above the reactor vessel, and eventually transferred to a spent fuel storage container. The design assumption embedded in this procedure was about water coverage. The OK-150 refueling protocol required that the reactor vessel and the refueling cavity above it remain flooded with water throughout the entire handling operation. The fuel assemblies, even after reactor shutdown, were generating decay heat. The water surrounding them served two simultaneous functions. It cooled the assemblies, preventing the fuel cladding from overheating and potentially failing, and it provided radiation shielding, preventing the gamma radiation emitted by the fuel assemblies from exposing the handling crew to lethal dose rates. The assumption was that this water coverage would be maintained continuously, that the water level in the refueling cavity would never drop below the top of the fuel assemblies during handling operations, that a specific interlock system, a sensor network monitoring the water level and designed to halt the handling machine if coverage dropped below a defined minimum, would prevent any handling operation from proceeding if the cooling and shielding water was not present in sufficient volume. The internal technical review that OKBM's Reactor Safety Engineering Group had completed before the Lenin entered service had identified a single question about that assumption. The question was not dramatic. It did not predict an accident. It asked whether the interlock system's sensor placement and response time were adequate to detect and halt a handling operation before fuel assembly exposure could occur if the water level dropped faster than the sensor's designed detection rate. The review concluded that the interlock system met its specified performance parameters under nominal conditions. It recommended further analysis under off-nominal conditions, conditions where the refueling cavity drainage rate might be higher than the design baseline assumed. That recommendation was logged, assigned a tracking number, and placed in the technical review archive. The follow-up analysis it recommended was never completed before the Lenin entered service. The first indication that the OK-150 refueling system had a problem exceeding its design baseline came not in 1967, but in 1965. During a scheduled refueling cycle on reactor number 1, technical personnel conducting post-maintenance inspection of removed fuel assemblies identified damage to the zirconium cladding on several units. The damage was not catastrophic. The fuel rods inside the damaged assemblies had not ruptured. The radioactive uranium oxide pellets had not been released into the primary coolant, but the cladding deformation pattern was not consistent with normal operational wear. It was consistent with a thermal event, with the fuel assemblies having been exposed for some period of time to conditions in which their cooling was inadequate. The incident was investigated internally. The investigation concluded that the damage had resulted from an anomaly in the water level management during the refueling sequence. The specific conditions that had produced the anomaly were not fully reconstructed. The technical documentation produced by the investigation was classified and returned to the OKBM archive. The refueling procedure for the OK-150 was reviewed. A supplementary procedural step was added, requiring manual verification of water coverage at 2 additional points during the handling sequence. The analysis did not revisit the question raised in the pre-service technical review about off-nominal drainage rates. The supplementary step addressed the symptom. It did not address the underlying question of whether the system's drainage characteristics under certain valve and pump configurations could produce a coverage loss rate exceeding the detection capability of the interlocks. The Lenin returned to Arctic service. The 1965 incident was not reported to the Soviet Civilian Nuclear Regulatory Authority. It was not reported through the formal reporting channel designated for nuclear incidents on civilian vessels. It was handled entirely within the OKBM Navy Technical Coordination Structure and classified at the level that prevented its details from reaching any organization outside that structure. The individuals who had performed the 1965 refueling operation were not the same individuals who would perform the 1967 operation. Standard personnel rotation had moved them to other assignments. The classified incident report describing what had been observed in 1965 was accessible within the OKBM technical system. It was not part of the operational briefing package provided to the engineering team assigned to the Lenin's 1967 maintenance cycle. The The supplementary procedural step added after 1965 was incorporated into the current procedure manual. The reasoning behind it, the fact that it had been added because something had gone wrong, was not part of the documentation the 1967 team received. They knew what to do. They did not know why one of the steps existed. February 7th, 1967. The refueling operation on reactor number 2 proceeded through its initial phases within documented parameters. The reactor had been shut down on schedule. Decay heat cooling had been maintained for the required period. The water level in the refueling cavity had been verified at the specified level before the handling machine was engaged. The first several fuel assemblies were removed from the reactor vessel and transferred to intermediate storage positions without anomaly. The sequence that produced the accident has been reconstructed from the classified investigation's technical findings, from partial testimony obtained during civil proceedings brought by affected personnel, and from accounts provided to Russian investigative journalists by former OKBM engineering personnel in the late 1990s. The full unredacted investigation report has never been officially released. What follows represents the reconstruction that emerges from those sources, which are consistent with one another on the essential technical sequence, even where they differ on specific procedural details. At a point during the handling operation, the refueling cavity water level dropped. The drop was not catastrophic. It was not a sudden drainage event. It was a gradual reduction driven by a combination of factors. The thermal load from the decay-heated assemblies warming the cavity water and producing evaporative loss at a rate slightly above what the makeup water system was compensating for, and a valve configuration in the cavity drainage path that was not fully closed, not through any deliberate action, but through mechanical wear in the valve seat that allowed a slow seepage. The system's sensors did not register as a fault condition. The water level dropped below the top of several fuel assemblies positioned in the intermediate storage locations within the refueling cavity, not in the reactor vessel itself, but in the cavity above it, where they had been placed during the handling sequence. These assemblies were generating decay heat. They were no longer covered by water. Their cooling was no longer adequate. The zirconium cladding on those assemblies began to heat. Zirconium has a specific thermal threshold above which it reacts exothermically with steam, with water vapor produced by the heated surface in contact with residual moisture. The zirconium water reaction produces hydrogen. It also produces additional heat, which accelerates the reaction. The cladding on several assemblies failed. Fuel pellets were exposed. Fission products contained within the uranium oxide ceramic were released into the water and steam environment of the refueling cavity. The primary circuit boundary had not been breached. The reactor vessel itself was intact. What had occurred was a fuel damage event in the refueling cavity. A space connected to the primary circuit, and that, once contaminated with released fission products, spread that contamination through the portions of the primary system it communicated with. The extent of contamination was significant. The number of fuel assemblies with damaged cladding, according to reconstruction from available sources, was between 30 and 60, a substantial fraction of the reactor's total fuel load. The decision made by the facility's senior technical management in the hours following discovery of the damage was to flood the refueling cavity and the connected reactor spaces with water to halt the thermal progression and contain the spread of contamination. This decision was technically sound as an immediate emergency response. It also introduced a complication that the facility was not equipped to resolve. The water used for flooding became contaminated with fission products from the damaged fuel. The primary circuit of reactor number 2 was now filled with heavily contaminated water. The reactor could not be returned to service. The contamination could not be removed through any filtration or decontamination process available at the Murmansk facility. The Lenin, with reactor number 2 in a condition from which it could not be recovered on site, continued to operate on its 2 remaining reactors, while the question of what to do with reactor number 2 was debated inside the classification wall of the OKBM Navy technical structure. The classified investigation began immediately. The commission assembled by the Ministry of Medium Machine Building and the Ministry of the Merchant Marine had access to the OKBM archive, including the 1965 incident report and the pre-service technical review that had raised the question about drainage rates and interlock response times. The Commission reviewed the refueling procedure in force at the time of the accident, the maintenance records of the valve and the cavity drainage path that had contributed to the water level drop, and the personnel records establishing which engineers had received which briefings before the 1967 operation began. The Commission's technical conclusions, as reconstructed from sources who have reviewed portions of the classified documentation, were specific on 3 points. First, the OK150 reactor's refueling cavity water management system had a design characteristic, the combination of the drainage path valve specifications and the makeup water system's compensation rate, that under certain combinations of thermal load and valve wear could produce a water level reduction rate exceeding the response time of the automated interlocks. This was precisely the question the 1965 pre-service technical review had recommended for further analysis. That analysis had not been completed. The 1965 fuel damage incident had been caused by this characteristic. The 1967 accident had been caused by this same characteristic, which had not been corrected between 1965 and 1967. Second, the classification of the 1965 incident report had prevented its operational implications from reaching the 1967 maintenance team through normal engineering communication channels. The supplementary procedural step added after 1965 provided a partial mitigation. It did not prevent a recurrence because it addressed coverage monitoring behavior rather than the underlying drainage rate characteristic. Personnel performing the 1967 operation did not know they were performing a procedure with a documented predecessor failure. If they had known, their approach to valve verification steps and makeup water monitoring might have been different. They were not given the opportunity to make that judgment. Third, the water management system of the OK150 required design modification to address the drainage rate characteristic. Specifically, the drainage path valve specifications needed to be tightened and independently verified at each maintenance cycle, and the makeup water compensation system needed to be modified to provide a higher flow rate reserve to address the thermal evaporative load at the upper range of the decay heat curve. These modifications were achievable without fundamental redesign of the reactor system. The Commission's findings were classified at the highest level of state secrecy applicable to nuclear facilities. The families of personnel who had received radiation exposure during the recovery operations were not provided technical information about what had occurred. Naval and merchant marine officers with access to the classified findings were bound by security oath. The engineering vulnerability documented in the pre-service review, the 1965 incident that had demonstrated it, and the 1967 accident that had confirmed it, none of it reached any public domain during the Soviet era. The physical problem of what to do with reactor number 2 had no simple solution. The reactor vessel and the refueling cavity were contaminated with fission products at levels that precluded the conventional decommissioning approaches available to Soviet nuclear engineering in 1967. Decontaminating the primary circuit and cavity to conditions where maintenance personnel could safely access them was not achievable with the technology and facilities then available. The decision reached by the responsible authorities, a decision made inside the classification wall and not subject to any external review by civilian, environmental, or nuclear regulatory bodies, was to remove reactor number 2 along with reactor number 1, which had sustained the 1965 damage, from the Lenin entirely. The 2 damaged reactor compartments would be extracted at the Sevmash shipyard in Severodvinsk. The Lenin would be refitted with a new, redesigned reactor system. 2 OK900 reactors replacing the 3 OK150 units, with the design modifications the Commission had recommended incorporated into the new plant from the outset. The extracted reactor compartments, sealed steel structures containing 2 damaged OK150 reactors, their associated primary circuit hardware, and the contaminated water that filled them, were transported by barge to a disposal site in the eastern Kara Sea. They were sunk in Tsivolki Bay at a water depth of approximately 30 meters. The disposal was authorized under a classified Soviet naval protocol for the disposal of radioactive materials that had no equivalent in any international treaty framework of the period. No notification was provided to any international body. No environmental impact assessment was conducted. The location of the disposal was classified. The Kara Sea received not only the Lenin's reactor compartments in subsequent years. The classified Soviet radioactive waste disposal program used a network of sites across the Barents and Kara Seas to sink damaged reactor components, liquid radioactive waste containers, and entire reactor-equipped submarine hulls whose dismantlement was not feasible using available technology. The Lenin's compartments were among the first, but far from the last. The Lenin returned to Arctic service in 1970, operating on its rebuilt reactor plant. The OK-900 reactors incorporated the drainage rate corrections and makeup water system modifications the Investigation Commission had specified. The refueling cavity water management system was redesigned with the faster responding interlocks the original pre-service review had recommended analyzing. The refitted Lenin performed reliably for the remainder of its operational service life, which extended to 1989, 30 years after commissioning. The modifications that made it reliable in its second phase of operation were the direct product of understanding the failure mode the original design had embedded and the 1967 accident had demonstrated. That understanding was entirely classified. The icebreaker that operated in full public view, shown to foreign dignitaries, featured in Soviet documentary films, presented as evidence of Soviet technological leadership in Arctic navigation, carried the evidence of its own classified failure history in the welded seams where the replacement reactor compartments had been fitted and in the modified valve specifications of its new primary water management system. The partial disclosure that eventually emerged followed the same trajectory that would characterize Soviet and Russian nuclear transparency throughout the late Soviet and early post-Soviet period. Not official acknowledgement, not a government decision to release classified findings, fragments, testimony from former personnel speaking anonymously to journalists operating in the relatively open media environment of the late 1980s and early 1990s, civil litigation by individuals seeking compensation for radiation exposure, who compelled partial disclosure through court proceedings, and one specific international trigger. In 1993, a Russian government commission chaired by Alexei Yablokov, then an advisor to President Boris Yeltsin, published a report on the Soviet Union's history of radioactive waste disposal at sea. The Yablokov Report, as it became known, was the first official Russian government document to acknowledge the systematic dumping of nuclear materials in the Barents and Kara Seas. It listed disposal sites, approximate quantities of radioactive material, and the general categories of objects disposed of. The Lenin's reactor compartments appeared in its inventory. The report confirmed that the disposal had occurred. It did not provide the technical details of why the compartments had been damaged or what the accident investigation had documented. The Yablokov Report created the framework within which former OKBM personnel and former Lenin crew members could speak with greater openness to journalists without appearing to unilaterally breach their security oaths. In the years following its publication, technical details of the 1965 incident and the 1967 accident began appearing in Russian naval and nuclear history publications, initially in generalized form and progressively with greater specificity as more former participants provided accounts. The picture assembled from those accounts confirmed what the classified commission had found. The drainage characteristic of the OK-150 refueling cavity system had been the root cause of both incidents. The 1965 event had been reported within the classification system, had generated a procedural modification, and had not generated a design fix. The 1967 event had reproduced the same failure mode against a backdrop of personnel who did not know a predecessor event had occurred. The design fix implemented in the OK-900 plant, the modifications that should have been incorporated into the OK-150 from the outset, was exactly what the pre-service review had identified as the necessary follow-on analysis. The families of individuals who received radiation exposure during the 1967 accident and its recovery have sought through Russian courts and through the European Court of Human Rights to obtain full technical disclosure of the medical and environmental data associated with the event. The specific dose assessments and long-term health monitoring data that would allow an independent evaluation of the exposure consequences remain within classified archive systems that the Russian government has maintained under continuing security classification designations reassigned from Soviet to Russian Federation authority. Some former workers have received compensation through administrative proceedings. The full medical records have not been released. The reactors sunk in the Kara Sea did not remain a contained environmental problem. 30 meters of water is not a barrier to the gradual corrosion of steel in a marine environment. The reactor compartments of the Lenin, along with the dozens of other nuclear objects disposed of in the Kara and Barents Seas through the Soviet disposal program, are corroding. The rate of corrosion and the rate at which radioactive materials are being released into the surrounding water column has been the subject of ongoing Norwegian-Russian joint monitoring conducted since the mid-1990s under a bilateral environmental cooperation framework. The monitoring has detected elevated concentrations of cesium-137 and other fission products in water samples taken above known disposal sites. The concentrations are measurable. They are, as of the most recent publicly available monitoring reports, below the thresholds that would constitute an immediate public health emergency for the fish populations of the Barents and Norwegian seas. They are not zero. They are increasing over time as corrosion progresses. The full inventory of radioactive materials in the Kara Sea disposal sites has not been publicly confirmed to the satisfaction of independent nuclear safety organizations. The Russian government has provided the Joint Monitoring Program with documentation of disposal site locations and general material categories. Independent verification of the completeness of that documentation is not possible without access to the classified disposal records of the Soviet program, which have not been released. The Lenin itself was decommissioned in 1989 after 30 years of Arctic service. It is preserved at a pier in Murmansk as a museum ship, the world's first nuclear-powered surface vessel, open to the public, a monument to the extraordinary ambition of the Soviet nuclear engineering program that produced it. Visitors to the museum can tour the engine rooms and observe the OK-900 reactor spaces that replaced the original OK-150 plant after the 1967 accident. The ship that stands there is not entirely the ship that first broke Arctic ice in 1959. Its reactor plant was replaced. The reactor compartments of the original plant are 1,800 kilometers to the east, in approximately 30 meters of water in the Kara Sea, corroding in darkness. Naval and nuclear engineers who have studied the Lenin incident in the decades since the partial disclosures of the 1990s have identified a pattern in the accident sequence that is consistent with findings from major nuclear facility incidents across multiple countries and reactor types. The pre-service technical review identified the question. The question was logged. The follow-up analysis it required was not completed before the vessel entered service. An incident occurred that was consistent with the unresolved question. The incident was classified in a way that prevented its operational implications from being distributed through normal engineering communication channels. A procedural modification was implemented that addressed a symptom without addressing the underlying system characteristic. The system was returned to operation. The same failure mode reproduced itself under slightly different conditions, against personnel who did not have the benefit of the preceding incident's operational lessons. This is not an exotic sequence. It appears in the records of 3 Mile Island, in the analysis of the Chernobyl disaster, in the investigation of the Challenger accident, in the forensic review of virtually every major engineering failure where a prior warning signal existed and was processed within an institutional structure that classified, compartmentalized, or procedurally addressed it without resolving the underlying engineering question. The Soviet nuclear engineering establishment of the 1960s was not uniquely negligent. It was operating within institutional structures, classification frameworks, and organizational information flows that were optimized for capability development and operational security, and were not optimized for the distribution of failure mode information across the boundary between design organizations and operational personnel. Those structural characteristics are not unique to the Soviet system. They exist in every large technical organization managing systems at the frontier of engineering capability. what is specific to the Soviet nuclear program, and what the classification of the Lenin's accident and the Kara Sea disposal records demonstrates is the extent to which those institutional characteristics were reinforced and protected by a state security apparatus that had both the authority and the organizational incentive to prevent external scrutiny from reaching the failure modes the system had produced. The OK-150 reactor's refueling cavity drainage characteristic was a solvable engineering problem. The commission that investigated the 1967 accident specified the solution. The solution was implemented in the OK-900 design. The modified plant worked. The engineering knowledge required to prevent the 1967 accident existed within OKBM before the 1965 incident. The institutional structures governing how that knowledge moved, or did not move, between the design archive, the operational briefing process, and the people performing the refueling sequence are what transformed a solvable problem into a repeated accident. The Lenin continues to float at its Murmansk pier. School children tour its passageways. Its reinforced bow is a monument to the engineering audacity that built the world's first nuclear icebreaker. The ship that stands there is not the failure. The engineering achievement of the OK-150 program was genuine. The Lenin achieved its operational mandate. The Northern Sea route it opened has carried a significant fraction of Russia's Arctic logistics for 60 years. The lesson the classified investigation documented, and that the Soviet state buried inside archive systems that have still not been fully opened, is not about the difficulty of nuclear reactor design. The OK-150 was a capable machine. Its designers were serious engineers working at the frontier of what was possible. The lesson is about the distance between identifying a question and answering it, about the institutional consequences of classifying failure mode information in a way that prevents it from reaching the operational personnel who need it, about the specific, reproducible danger of implementing a procedural modification to address the symptoms of an unresolved engineering question without addressing the question itself. That distance between the pre-service review that asked about drainage rates in 1959 and the accident that demonstrated why the question mattered in 1967 was not large. It was a single completed analysis that had been recommended and never performed, a single information pathway between a classified incident report and an operational briefing package that was never connected. In that distance, fuel assemblies overheated. Cladding failed. Contamination spread through a primary circuit that was never supposed to be contaminated. 30 men received radiation doses that were classified for years. 2 reactor compartments were removed from a ship and sunk in a sea that Norway and Russia now monitor jointly under a bilateral agreement that would not have been necessary if a question asked in 1959 had been answered before the Lenin went to sea. The ship that solved the Arctic navigation problem is a museum. The reactors it carried when it first solved that problem are an environmental legacy the Kara Sea will hold for centuries. The engineering lesson those reactors represent, the specific, documented, pre-identified vulnerability that the 1967 accident confirmed, was available to the institutions responsible for it from the first day those reactors turned their fuel to heat. It was not acted on, the files were locked, and the sea received what the institutions could not bring themselves to account for publicly: